All right, starting our last lesson here in our topic on rigid motion transformations, lesson 6, combining motions. A little warm-up activity to get started, just finding the distance between 2 points. Now, the key here, if we notice on each one of these examples, 1 through 4, is they either have an x value in common or a y value in common. So the distance between them is simply going to be the distance between the one variable that is not the same. So for instance, on number 1, the 3's, the y values are the same. So the x values, the distance between the x values is the distance between the 2 points. So the distance, if we think of a number line, for instance, between 2 and -5 is 7 units. For number 2, the x values are both the same, so the distance between them is going to be the difference between the y values. So again, thinking along the number line, the distance in units between -4 and 8 would be 12 units. Same thing for 3 and 4. For 3, the distance between them is going to be the difference between these y values, and the distance between -2.5 and 5 would be 7.5 units. And one more, for number 4, the y's are the same, so the distance between the x values is going to be the distance between the 2 points, and the distance between -8.2 and -4.3, if we subtract those, would be 3.9 units. And it all disappeared on me. But you can go back, rewind the video. I don't know why it's still doing that. Every time I try to change the screen size, it's deleting before. But rewind the video if you didn't have those quite filled in, and you can go back and fill those in. Again, it was 7 units, 12 units, 7.5 units, and 3.9 units. All right, our goal is here to use coordinates to identify what rigid motion transformations have taken place, determine a sequence of rigid motions, which is a little trickier, and generalize the effects of rigid motion transformations on the coordinates. Okay, again, key topics being, or key terms being congruent line segments and congruent angles. All right, so moving on to the next page here where it says going backwards. It says the pre-image and the image of three different single transformations are given. Determine the transformation that maps the pre-image, the labeled figure, to the image. Label the vertices of the image. All right, so if we are looking at A, for instance, what we are looking at there is a reflection. Okay, if we test the reflection over the y-axis rule, which is where xy becomes -xy, that's exactly what's taking place here. So for instance, A is at the point 3, 5. Well, the A of our new image is at the point -3, 5. So it has followed that reflection rule. So here would be the new A, new D, new B, and new C of our reflected image. For B, what we have there, you got to kind of pay attention to the angles of those lines, the difference between them. We don't have a reflection, which at first glance, that might be what you think, but you notice this side length here is corresponding to this side length based on the change from point to point. We're going down 2 units, right 2 units, down 2 units, right 2 units. So it's not reflected. Reflected, that would be flipped to the other side. What we have here is simply a translation. It has been translated to the left. And if we count units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. So it is translated left 10 units. So if you're thinking of a rule we'd have there from the original point, to go left, we're moving in the negative direction. So it's x minus 10 y to find your new coordinates. Okay, moving on to the next page, we got one more of these. C What we're looking at on C is we have a rotation. Now, as far as trying to figure out what rule to check, remember we talked about in our rotations lesson that every time we move one quadrant, we're moving 90 degrees. So since this moved 2 quadrants, the first thing I would check is our rule for translating 180 degrees. And when we check that, the 180 degree rotation rule, it is xy becomes negative x, negative y. So if we test one of the points, let's say D, and our pre-image is at the point 2, 3. If this were to be rotated around to this corresponding point here, we'd find it's at negative 2, negative 3. And each point would correspond as well to find that that matches up to have that rotation of 180 degrees. So this would be your new point D. This would be our new A, B, and our new C. All right, on the next page, where it says Activity 6.1, Congruent Statements. Again, there over on the left side, identifying that key term. Congruent line segments are segments that have the same length. Okay, so it says you've determined that if a figure is translated, rotated, or reflected, the resulting image is the same size and same shape as the original. Therefore, the image and the pre-image are congruent. So how is triangle ABC transformed to create triangle DEF? Well, if they're naming it ABC and they're saying it is creating DEF, we know that A is corresponding to D, B is corresponding to E, and that C is corresponding to F. So this figure hasn't been flipped, hasn't been necessarily just translated because it has changed orientation. So what we have here is we have a rotation. Now, to what degree, we don't know just because we're not looking at a coordinate grid, but we do know for a fact that has been rotated because the orientation has changed, moving it counterclockwise to the left. Okay, and the worked example here says because triangle DEF was created using a rigid motion transformation, triangle ABC and the triangles are congruent. Therefore, corresponding sides and corresponding angles have the same measure. So that's the case in congruent figures. So if the length of segment AB, so length of segment AB up here is equal to the length of the segment DE. Okay, you might see it written like this. AB is equal to DE. The distance between AB is equal to the distance between D and F. The measure of AB is equal to the measure of DE. So the measure of line segment AB is equal to the measure of line segment DE. Okay, and if the sides of two different triangles are the same length, for each example, the length of the side in the triangle ABC is equal to the length of the side DE in triangle DEF. These sides are said to be congruent. Okay, so this symbol right here, we're saying it looks like your equal sign with your little squiggle above it. That is a sign we read as congruent. So line segment AB is congruent to line segment DE is how we will read that. So trying to keep that on the same screen. 2 down on the next page. So if we want to write congruent statement for the other 2 sets of corresponding sides, well, the other 2 sides would be line segment BC is congruent to line segment EF, and line segment AC is congruent to line segment DF. Okay, likewise, corresponding angles have the same measure. They are congruent angles. Congruent angles are angles that are equal in measure. So going back to that, congruent means they are equal. So similar in this example here, if measure of angle A is equal to the measure of angle D, the relationship can be expressed using these symbols. Measure of angle A is equal to the measure of angle D is how we would read that. If the angles of 2 different triangles are equal in measure, for example, the measure of angle A in triangle A is equal to the measure of angle D in triangle DEF, these angles are said to be congruent. Okay, we keep going back to that. All these rigid motion transformations are maintaining congruency. So again, using that congruent symbol, we would read this as angle A is congruent to angle D. So again, if we want to write congruency statements for the other angles, we could say angle B is congruent to angle E, and angle C is congruent to angle F, going back to that original triangle. When I scroll back up, you can take a look at that. So B to E, we said. So again, here was angle B, here was angle E. Those corresponding angles would be congruent. Okay, you can write a single congruent statements about a triangle that shows correspondence between the two figures. For triangles, its activity ABC is corresponding or congruent to triangle DEF. Write two additional congruent statements for these triangles. So the key here is when you write congruency statements, the order of those vertices needs to be congruent angles. So if A is first, it needs to be corresponding to the first letter in the next triangle as its corresponding angle that's also congruent, which is angle D. So as we rotate this through to write other examples, we could say triangle, if we start with the B, BCA is congruent to triangle. Now we'd start with the E, EFD. Or if we started with a C, we could say triangle CAB is congruent to triangle FDE. And those would be two other congruency statements talking about the same triangles. Okay, they would all be correct. They would all mean the same thing. All right, next activity 6.2 says using rigid motion movements to verify congruency. You can determine if two figures are congruent by determining if one figure can be mapped onto the other through a sequence of rigid motions. Therefore, if you know the two figures are congruent, you should be able to determine a sequence of rigid motions to map one figure to the other. All right, so if we look at number one, we see the original figure, say WCT, or TWC as they identify it in question A, and we're trying to figure out how we got to that next figure. Again, your first hint here about what might have happened is that orientation of that triangle has turned. Okay, so for that to happen, we needed to have had a rotation. So if I'm looking at rotations, also notice you've moved one quadrant. So we're looking at 90-degree rotation. And it has moved in a counterclockwise direction. So 90 degrees counterclockwise would be my hypothesis to test here about are these congruent. And that 90-degree counterclockwise rule, if we go back to our rules, is that XY becomes negative YX. So if we test one of the points, point C, which looks like it should correspond to point K if that is rotated, point C is at negative 4,3. So that means that corresponding point, which is point K, not even looking at what it is mapped there, if we follow our rule, it should become negative 3, negative 4, which matches up exactly to what we have there. Okay, and if we test the other points, you'd find the same thing. So we can say they are congruent. We could say triangle TWC is congruent. If we're starting with the T, if we rotate that around, that's congruent to the P, angle P. So we'd say triangle PMK. Okay, write congruent statements to identify the angles. So just follow the order that we wrote that triangle in. So angle T is congruent to angle P. Angle W is congruent to angle M. And angle C is congruent to angle K. Okay, and same thing we could do for the sides. So we could say side TW. So this side right here, and I'm going to mark in blue, is going to correspond to that side there. So that would be congruent to side PM. And the other two, we could say side WC is congruent to side MK. And one more, the other side would be TC is congruent to side PK. Okay, as long as we're getting the idea of congruent, corresponding sides, especially identifying them when you rotate a figure, can get really tricky. Being able to match those up. All right, next example. So looking at our figure in figure 2, first thing I notice is the orientation hasn't changed, but it appears to me like we have flipped this over the x-axis. So I would test the rule first as a hypothesis as a reflection over the x-axis. And if we follow that rule is xy becomes x negative y. So again, if we test one of those points, I'm going to test these two. Erase that so I can see what their names are. So we got point R, which is at 6, 1. And I'm going to say it corresponds to point Q. So if we follow that rule, it should become 6, negative 1. And if we look back at what it is, yes, it matches up. And if we test another one, the other 2 points, you're going to find the same thing. So yes, they are congruent. Again, a triangle congruency statement, we could say triangle TRG is congruent to triangle ZQV. And again, we could do the same thing to identify the angles. I'm going to just do one of the angles and one of the sides and let you take the time to match up the other ones to make sure you see fit. So for angles, we could say angle T is congruent to angle Z. So again, if we look at how the triangle, if we wrote the triangle congruency right, T to Z. So you should be able to match up R to Q and G to V. Okay, then similarly with sides, we could say side length TR is congruent to side length ZQ. Okay, and again, you could match up the other ones as well. All right, moving on to our next page. Okay, what we have here, it looks like we're probably going to have, in first glance, I know we're definitely looking at a reflection, it looks like. And then we're probably going to have some sort of translation. The orientation doesn't match up well for having just a rotation. So I'm looking at probably a reflection and a translation. So just to test this, if we're looking at, say, starting with, I'm going to say this is triangle 1. If we're starting with that triangle KRH, first trying to get it over to that figure, I'm going to look at thinking of reflecting it this direction. So if we reflect it that direction, our reflection rule across the y-axis is that xy is going to become negative xy. So if I take those points, this point right here is at 8, 0. It should reflect and go to negative 8, 0. Point R is at 6, negative 4, so it should reflect and go to negative 6, negative 4. And then point H looks like it's at 1, negative 5, so it should reflect, trying to erase here, so it should reflect and go to negative 1, negative 5. So there's our triangle. Now that does get us to the proper orientation of the other one. of ADJ. So it looks like we probably now have a translation that it is moved up. And when we flip these to corresponding vertices, this would be K, R, H. We'll keep that in mind when we name these triangles here in a minute. So if we count the number of units that's moved, 1, 2, 3, 4, 5, 6. So it looks like it's also been shifted up 6 units. 1, 2, 3, 4, 5, 6. So there we have it. So if we correspond those triangles now, we could say triangle ADJ is congruent. If we go in the same order, we would be at KRH. So K to R to H. So there we would have those congruent triangles. So the sequence of translations, we said reflected across y-axis and then translated up 6 units. Okay, if you reverse the order of the transformations that you use in part B, does the order map to one figure to the other? Yes. Anytime you reverse the transformations, as long as you have the correct series of transformations, we would get back to the original figure. They would work. Okay, explain why it's not possible to map one figure onto the other using only rotations and explain why it is not possible to map one figure onto the other using only rotations and translations. Because the orientation required a reflection. We could not just rotate that using any of our rules and get to that figure, that new figure. All right, next one, analyze the two congruent triangles, write a congruency statement. Now, for purposes of assessment, you will only be asked to reflect over an axis, but this coordinate grid, you notice, does not have an axis. So we do have congruency here, and to identify the sequence of transformations, first thing I want to do is I'm going to talk about a reflection, and if we find that midway point between these 2 points, we can reflect across that line. So, for instance, this point is 4 from there, this point is 4 from that line of reflection. Point B is 8 from that line of reflection, this point is 8 from that line of reflection. So point A, same thing. It is 8 from that line of reflection, so if I move it over here, there's my new triangle reflected. So there's our first transformation to get closer. From there, we can just reflect it across that line. We could call it line BC or line UG. So they are congruent. So if we want to write a congruency statement, we could say triangle ABC is congruent to triangle TGU. My triangle shifted a little bit on me. Let me redraw that because that's going to make it confusing. There we go. All right, so there's our congruency statement for the triangles. The series of translations we had was reflected. Let me redraw that line too. Notice that was off. So here was that line halfway between them. So reflected across a vertical line halfway between, then reflected across segment UG. Again, that was that segment right here. We flipped over that segment and reflected. So reflected across segment UG. Okay, C again, if you reverse the order of the transformations that you used in part B, does it map to one figure to another? Again, yes. If you reverse the order, you're still going to map it. Can you determine a way to map one triangle onto the other in a single transformation? Technically, yes. If we could determine a center of rotation, we could probably get there based on rotations. But for our purposes, if we talk about just reflecting it now around the origin, I'd consider most likely for our purposes, no. But specifically, to be exact, we will say yes if you can determine a center of rotation. But as I said, for our purposes that will be assessed over, our point of rotation is going to be the origin we're going to work with. It's just this coordinate grid does not have an X and Y axis on it. All right, next page. Analyze the two congruent rectangles. Identify a sequence of translations, reflections, and or rotations that can be used to verify the two rectangles are congruent. Okay, so if we're looking at this, we know for sure that the orientation has changed. So we'd have a rotation, and then it would be translated down. So it would be rotated to turn this way. We would need to find that center of rotation. Again, we're not going to get into determining a center of rotation. We're going to always use the origin. So I'm not going to get too specific on this problem, but it could be rotated that way and then translated down. Looks like 6 units. We'd move that down to get it on top of it. Okay, but again, we're not going to spend too much on time on that one because we're not going to determine centers of rotation. We're going to be using the origin. All right, last little activity says for triangles in this activity, PQR and triangle JME is congruent to triangle DLG. It says suppose the vertices PQR are those numbers given, 4, 3, negative 2, 2, and 0, 0. Describe the translation used to form each triangle. All right, so if we're looking at A, so from A, point P went from 4, 3 and became 0, 3. Okay, point M went from Q at negative 2, 2. I think I've lost my page here. So I lost track of what page I was on. Went from negative 2, 2 to negative 6, 2. And point E went from negative 4, or from 0, 0 to negative 4, 0. So what looks like, if you look at all those X's, all the Y's have stayed the same. All the X's have gone down by 4. From 4 to 0, from negative 2 to negative 6, and from 0 to negative 4. So our move has been a translation using the rule X minus 4 Y. The X has gone down by 4. Okay, if we look at the B, again, looking at those points that have changed. So from P to D, the X's stayed the same. And it looks like the Y went from 3 to 5.5. So that's an increase of 2.5. So let's see if that's the same on the other ones. Q from negative 2, 2 to L, negative 2, 4.5. So again, that matches up. So it looks like we've had another translation. And our X has stayed the same, and our Y has increased by 2.5. So there would be our translation rule. All right, we'll probably do 2 more of these and then go ahead and get to the back page, just defining the different changes we're looking at. All right, 2, suppose the vertices triangle PQR, 1, 3, 6, 5, and 8, 1. We're going to figure out the rotation used to form each triangle. So we know we're dealing with rotation. So to get from P, look at the first one, 1, 3 to negative 3, 1. So to me, that looks like we've used a rule of X, Y becoming negative Y, X. So if we go back and look at our rules, that's a 90-degree counterclockwise rotation. And misspelled counter. Let's try that again. Counter clockwise rotation. Okay, if we look at D, or letter B, look at that first point again. D became -1, -3, and we started at 1, -3. So what's happened there is we've had a rule used that is -x, -y from the original point. Well, to get -x, -y, from a rotation, we've rotated 180 degrees. Remember, with 180, it doesn't matter if we go clockwise or counterclockwise because we're getting to that quadrant across from it in a straight line. All right, we'll do one more, and then, like I said, we'll skip to that back page. If you want to try number 4 and fill that in, you can. 3, suppose the vertices PQ of triangle PQR are 12, 4, 14, 1, and 29. Describe the reflections, we know we're reflecting, to get our new points. So again, let's just check out the first point, try to figure out our rule, 12, 4 to -12, 4. Well, that looks like we've gone from a rule of xy becoming -x. Y. The x changed negative. If we go to our reflection rules, that tells us reflected across the y-axis. And if we check the other points, you would find the same thing. So one more, B. So now we've gone to 12, -4. So that looks like we've now used a rule of taking xy and becoming x, -y. And that corresponds to a reflection across the x-axis. All right, so as I mentioned, try number 4. 4 is a little tougher. Once you do it, I'll go ahead and give you the answers. If you want to pause the video and try it, you should find that you've used a rule, 2 transformations happening, of xy first, reflected across the x-axis, becoming x, -y, and then it's translated up 5 units. So the final rule that happened was x plus 5, -y. So reflected, I'm going to put reflected, x-axis, and then I'm going to put up arrow, 5 units. And then for B, again, if you've tried that one, again, these double rules are a little tricky. You'll find that the rule that's happened here is xy was first rotated 90 degrees, a rule of y -x, and then moved down 3, it looks like. Yep, so down 3. So our final rule, you'd have y -x and then -3. So rotated and put rot 90 degrees clockwise. And then down 3. So those are a challenge. Those are tough ones. If we can get those, you're doing really well, because you combine those transformations to figure out, especially when you're not looking at the figure, it can get very tricky. Okay, leading to 5, probably the most important things we keep reiterating are the images that result from a translation or rotation or reflection, always, sometimes, or never congruent. They are always congruent. Gets back to all of our rigid motion transformations do not change congruency. All right, final page is filling in. Suppose you have a point xy undergoes a rigid motion transformation. The new possible coordinates are shown. Assume C is a positive rational number. So we're going to fill these in under our 3 possibilities: translations, reflections, and rotation. So again, translations are always going to just have a plus or minus to the x. So x plus c, x minus c, y plus c, y minus c. So if we fill those in, translations we could have x plus c, comma y. Could have an x minus c, comma y. We could have an x, y plus c, and we could have an x, y minus c. So our description, this would be right c units. This would be left, when we have x minus c, left c units. The next two, y plus c, would be up c units, and y minus 6 would be down c units. So there would be our 4 possible translation rules we're looking at. And we move over to reflections. Reflections, we only got 2 possibilities over the x or y axis. So we could have x minus y. That's reflect over the x-axis. Or we could have a negative x, y. And that's reflect over the y-axis. And the way I remember those 2 rules is if I'm reflecting over the x-axis, notice the x stayed the same, is with the y changed. If I'm reflecting over the y-axis, the y stayed the same, the x changed. Okay, and then our rotation rules. We have, you could say, negative yx. Or actually, I'm going to put the other one first. I'm going to go in a certain order. I want to go in. Let's go y negative x. This is a 90-degree clockwise, which is also the same as 270 degrees counterclockwise. Okay, then we have negative y x. This is 90 degrees counterclockwise, or 270 degrees clockwise, because those both end you up in the same spot. And these are also on that rules sheet we wrote out. And then the final one, negative x, negative y. And this is a 180-degree rotation. And remember, with 180 degrees, it doesn't matter if we move clockwise or counterclockwise. Okay, so there's all the transformations we could see based on the rules we have talked about.